The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So what are we going to do today? So today, we are going to continue the discussion of, based on what we have learned from diffraction and also the interesting phenomena. And we are going to make connections to quantum mechanics and discussion in greater detail about this connection. And also, if time allows, we are going to cover a few results, a few information about gravitational waves as well. So last time we have discussed diffraction pattern coming from a laser beam, and we discussed about resolution. And you can see that this is the graph we see last time already in the lecture. Basically, all the point-like source coming through a single slit is going to be doing interference to each other, right? So basically, you see interesting pattern, which you have a central peak, and the total constructive interference happens at the center of the screen, and at some point you have a deep, which is actually where total destructive interference actually happen, and we were able to understand this with mathematics, which we learned from IO3. Another interesting result we found is that if we shoot a laser beam to the moon, all right, by now you should be able to conclude that it's not going to be a point on the moon. Instead, it's going to be a spot as large as the whole mystery state. All right, so that's actually another interesting result we found from the discussion last time. And finally, we are able to put together all the things we have learned from the last few lectures. Basically, you can have at the same time the effect of multi-slit diffraction interference, and also the effect of a single slit diffraction. All of them are put together, then you have this complicated but also beautiful pattern, which you will be able to observe on the screen. And basically, the point is that you are going to have, for example, in this case, 5-slit interference pattern, but that is actually modulated, the intensity is actually modulated by the pattern from a single slit diffraction. Okay? So that is actually what we have learned from the last lecture. Coming back to the original question, why do we study AO3, right? The reason is that we would like to understand, we would like to hear from the universe, right? So we cannot even recognize the universe without using waves and vibrations. So that's the cool thing which we have been doing here. And we have seen waves of matters. Right? So for example, here we have this water wave generator. You can see water waves. We have this Bell Lab machine, which you can see the coupled oscillator of multiple coupled oscillator, and they are doing their job together to form beautiful waves. And you can see those beautiful results from there. Last time, we also, and also including the last few lectures, we have been using this laser to produce interesting interference pattern and the diffraction pattern, okay? So that's the second kind of wave which we actually encounter. The first kind is the waves of matters. The second kind is waves of what? Waves of vector field, right? It's not matter anymore because this field, this oscillation of field, can also travel through vacuum, right? So that is actually a second kind of wave which we actually learn from AO3. They provide a completely adequate description of the nature, a description of the phenomena which we can actually measure, can see from the experiment we went over. So what I would like to say in the lecture today is that there are two kinds of completely different waves which we haven't talked about. The first one is the probability density wave, which I will cover that in a moment. The second one is gravitational waves. This is actually a space-time distortion coming from the motion of massive objects. And we would like to see what we can also learn from there using the existing knowledge which we have learned from matter wave and the vector field waves. And they are actually pretty similar to each other if you look at their behavior. So the first thing which I would like to discuss is light. So far, what is light? Light is like electromagnetic waves, right? So that's essentially what we have learned so far from L2 and L3. So they are like waves. They are waves, all right? On the other hand, in the 20th century, there are many, many crises going on, right? Okay, so the first thing which is happening is photoelectric effect. So this experimental result was actually first discovered by Hertz. So he found that if you want to kick one electron out of some material, or some charged material, it is easier if you use a high-frequency light compared to low-frequency light. Okay, so that's actually really strange, right? Because based on waves and also the intensity formula, what we really care, right? Intensity is proportional to the square of the electric field amplitude, right? So that's actually what we actually learned from the previous lectures. But what Hertz was saying is that the frequency also matters. Okay, so that's really a bit really strange. And Einstein actually came in and explained this photoelectric effect. Okay, so what he found is that this effect can be explained by viewing the light as small quantas, okay? And the light is actually not like waves anymore, but like quantas, small quantas, discrete ones, with energy proportional to the frequency, all right? Basically, the energy of those little quanta, or say we now call them photon, is actually equal to h, which is Planck constant, is some constant relate the frequency and the energy of the quantum. Okay, and with this explanation, the view is that the photons are like particles. And therefore, he can actually explain that, okay, if I measure the kinetic energy, the maximum kinetic energy of the electron, electrons which are kicked out from this photoelectric effect experiment, okay? I call it K max. What you are going to get is a formula like this. The maximum kinetic energy of electron will be equal to h bar nu minus phi. Phi is actually some kind of threshold which you need, or say some kind of energy which you need to overcome to kick one electron out of the material. Okay. So you can see from here that if the frequency of the light is too low, then this will never work because the kinetic energy the maximum kinetic energy will be below 0. Therefore, you cannot kick out of an electron. All right? But if the frequency is high, as shown by Hertz's experiment, it is possible, and also you can create energetic electron, have them kick out of the material. Okay? And this is actually verified by experiment, and that is actually why Einstein actually get the Nobel Prize in 1921. So let me tell you what the feeling here. The feeling here is that now things are really becoming more and more interesting because, first of all, we see really well the electromagnetic waves describe the behavior of the light. We see diffraction, we see interference. All those things can be explained by the beautiful mathematics which we have been employing to explain all those results. But here you can see that at the same time, the photons are very good tool or very good viewpoint to explain the photoelectric effect. So that's actually really surprising because that means you have suddenly both kind of explanation of the light, which should be describing the same thing, right? So now you are one idea is to describe them by waves. The other idea is to describe them by particles. And also at the same time, as we actually discussed in the previous lecture, we can do a two-slit experiment with a billiard board or with bullets. Suppose we do this experiment. We fire the balls or bullets through some source, and we have some kind of two-slit setup here, okay, so that the bullets or bolts can actually pass through. And then we were wondering what would be the pattern which we see from the detector in the right-hand side. Then basically what we see is the following. So basically we have a distribution of the balls from coming from slit number 1. And we have another distribution of balls which is actually coming from slit number 2. And I can call it P1 and the P2, which is actually the probability density distribution of the experimental result. And if the final result, or say if you just look at the distribution of balls without separating from the balls from slit number 1 and slit number 2, basically you get some distribution like this, which is a superpositional P1 and the P2 distributions. Okay, all these things doesn't surprise anybody, right? The experiment one, which we perform with, now instead of billiard balls, now we perform the same experiment with electrons. All right. And again, we have all those electrons pass through this two-slit experiment. As we actually see before, basically, again, we can actually separate electrons from the first slit, which I call it I1. And the electrons coming from the intensity of electrons coming from the second slit, okay, which I call it I2. Then basically, if you can identify and make sure that the electron is coming from one of the slits, you are going to get distribution like this. Okay? And of course, I can always write this I1 as some wave function psi1 squared, right? And I can always write this I2, which is the intensity as a function of position of the electron coming from the second slit. Okay, I can always write it down as psi2 squared. Okay, in the case of light, it's actually just proportional to the electric field, right? Okay. So if you accept this, and now you actually don't measure where the electron actually passed through when the electron from the source passed through this experiment, okay? We now don't measure if it passed through 1 or 2. Then the pattern becomes like this. You have something like this, which is actually very, very similar to the two-slit interference experimental result of the laser experiment. Right? As you can actually see from this experimental result, you see some kind of pattern. You have the peak, you have the valley as a function of position in the detector. And we can actually call this I12, which is actually when you don't measure or say you don't identify which slit the electron goes through, then you have the intensity, which is actually called I12. And what we actually found is that I12 is actually not I1 plus I2. Okay? What we found is that I12 is actually psi 1 plus psi 2 squared. Okay? So basically, we see interference pattern. And this will be equal to I1 plus I2 plus 2 square root of I1 plus I2 and the cosine delta, where the delta is the coming from the path length difference. Okay? So based on this experimental result, this is actually really surprising. First of all, electrons are arriving like a particle, right? Because we can see from this slide, okay? If you look at the upper left figure, you see doom, doom, doom. Every time you have something hitting the screen, and what is actually left over is a single hit on the screen, right? Therefore, the electrons are arriving like a particle, all right, producing a hit in the detector. On the other hand, what we are saying here is that before they hit the screen, okay, they are behaving like a wave. It has interference with itself like a wave. All right? So is electron a particle, or is the electron a wave? Strange. The answer is electron is actually neither of them in reality. Okay? So how about we actually do some more experiment to convince ourselves what is actually really going on? So what we could do, as I actually mentioned, I can still have the electron gun. I have electron source in the left-hand side. Again, I have this two-slit experiment here. Okay. Then what I'm going to do is to produce a light source here. Okay, I put a light source there. Okay, to shine the whole experiment. Okay, then I was wondering what is going to happen to the distribution. So if I first close the lower slit number 2, and only measure the intensity coming from slit number 1, then this is the distribution I get, which is I1. If I close the upper one and open only the lower one, I get the distribution, which is I2. Okay? And this light source is actually interacting with the electron. When an electron passes through this slit, what is going to happen is that you will see some scattered light coming from that slit. Therefore, you can know which slit the electron actually passed through, okay? And if I do this experimental result, if I block one of the slit, this is a distribution I1 and I2. And now I'm going to open both slits, and you will see light coming out of the slit when the electron pass slit number 1 or slit number 2. Okay? You can identify which slit for all the electron passing through this experiment. And the resulting distribution of electron on the screen is actually like this. It's actually like I1 plus I2. There will be no interference. Why is that? That is because you know very precisely which slit the electron actually passed through this experiment. Okay? And also, or say, we can say that, the electrons are actually disturbed, right? Therefore, they now behave like bullets or like billiard balls. Okay, so this is actually a bit strange, right? Maybe it is because the intensity of the light is too large. Therefore, it's changing the behavior of the electron. Okay, so what are we going to do now? Experimental result number 3 is to lower the intensity of the light. So what will happen if I lower the intensity of the light source so that we would like to see the behavior as a function of intensity, okay? So at some point, we will find that some of the electrons are not hit by a photon, or say there will be no scattered light of the electron when it passes through the experiment because the intensity of the light is too small, okay? And we already know from photoelectric experiment, light is actually also like quanta, right? So when the intensity is low enough, the effectiveness of the light source decreases, okay? Then the experimental result will be like what? Can somebody actually give a guess? Is that going to be like experimental result number 1? Or is that going to be like experimental result number 2? Anybody want to get? Very good. So the result, as I mentioned before, sometimes the electrons are detected, okay, by the light source. Sometimes the electrons are lucky. They pass through without get hit by a photon. Therefore, you cannot know which slit actually this electron went through. Therefore, the experimental result is that if I just lower the intensity of the light source, then what I'm going to get is a mixture of experimental result number 1 and the experimental result number 2. When I have the intensity low enough, going to really, really low intensity limit, the result will become experimental result number 1, because then you are not really detecting the position of the electrons. Okay? Finally, you can actually also suggest something else, right? So, okay, now I have low intensity of light. One way to lower the intensity is like what I was saying, right? The rate of the photon emission, I can make it lower and lower, all right? There's another way to do this. Experimental number 4, experimental result number 4. So what will happen if I use this formula, E equal to h bar nu equal to hc divided by lambda, right? Because nu is actually just c over lambda. What will happen if I, instead of lowering the rate of photon emission, I lower the energy of individual photon? How do I do that? What I could do is to lower the frequency of the electromagnetic wave of the light source, or say increase the wavelength of the light source. Okay, I can now, this is very nice because now I can keep the same rate so that I make sure all the electrons are bothered by the photon, right? Because I can emit very high rate. But at the same time, I can also lower the intensity so that the intensity is very, very low. Can anybody guess what is going to happen? Well, the result like experimental result number 1, when I go to extremely low intensity, or my result will be like experimental result number 2, because each electrons are bothered, are heated by the light source, by the light source, the emission from the light source. Anybody want to try? Just guess, no? 1 or 2, or a mixture of them. The guess is that it is going to be like 2, which is actually well motivated. Very good try. What is actually happening is that, okay, I can say, each electron are bothered by like many photons, right? So okay, those are disturbed. Therefore, it has to look like experimental result number 2. The answer may surprise you. The answer is that if I have the limit, lambda goes to infinity, nu goes to 0, what is going to happen is that no matter how high frequency of photon emission I have, I am going to get the result of experimental number 1. Why is that? That is because when the wavelength of the electromagnetic wave or the photon is going to infinity, that means you cannot resolve which electron, slit actually the electron goes through, right? Because if I draw the wavelength here, it's going to be like this, okay? If you observe some kind of light, actually scatter light from the electron, okay, it could come from both slits because the wavelength is too long, right? So if you go to infinity, then it's like you have a constant electric field there. It doesn't really actually help you to identify which slit the electron actually pass through. Okay, so therefore the interference pattern reappear. So this is really a crazy thing if you look at all these 4 experimental results. The conclusion from these 4 imaginary experiments is that it is not yet possible to tell the position of the electron, and also at the same time do not disturb it. Okay? If you were able to tell the position of the electron, then there will be no interference pattern. On the other hand, if your experimental setup have no ability at all to tell if the electron is coming from slit number 1 compared to slit number 2, then you are going to get interference pattern. There's another thing which I would like to make connection to the uncertainty principle, which we actually learn from wave and vibrations. So we have learned that Heisenberg's uncertainty principle this is actually purely coming from the property of the wave, if you actually remember the derivation which we have done in the previous lecture. So what this uncertainty principle telling us is that the standard deviation of the position times the standard deviation of the momentum, okay, is going to be greater or equal to h bar over 2 some constant. And how do we actually understand this from the electron experiment? That is actually highly related to the single slit experiment with electron. So what we could do now is to have a fifth experiment. I have electron source here, and I have a single slit, and the width of the slit is capital D. And we were wondering what is going to happen, what will be recorded by the small detector in the right-hand side. And by now, it should not surprise you that this will give you some kind of diffraction pattern, which is actually very similar to what we actually observe with laser experiment. Okay? So you can see that the electron, the momentum, now I would like to actually define my coordinate system. The vertical direction pointing upward is my x direction. Okay? So now if I take a look at this experimental result. So what this is actually telling us is the following. We know the position of the electron to an accuracy of the width of this slit, okay, which is D. Okay? So that is actually telling you about the uncertainty in of the position in the x direction. Okay? Now, this electron goes through, and they actually hit the screen, and each electron is having a single pass. Okay? If I look at one of the paths, the upper one, okay, what I'm getting is that there must be a momentum which is actually in the x direction when this electron goes through the slit and hit the screen. Okay? One interesting thing we learned from the deviation from last time is that let's look at the slide here. If I look at the left-hand side slide, if I have a very small slit, okay, D is small, okay, what does that correspond to? That corresponds to delta x goes to very small value case, okay? You have a very small delta x value. You are really sure where is the electron at some instant of time when it passed through the experiment, okay? Then what is going to happen? If you look at the right-hand side, the distribution on the screen, you will have a wide distribution of the central maxima peak will be very wide, right? So what does that mean? That means you have a wide distribution of momentum in the x direction, right? Therefore, that will give you, that is actually consistent with what is actually written here, Heisenberg's principle. Delta x times delta p will be greater or equal to some value. On the other hand, if I increase the width of the slit, the D is now large. As you are making a D larger and larger, what is happening is that the central peak, the width, is actually going to be narrower and narrower, right? That is actually also consistent with what we have learned from Heisenberg's uncertainty principle. When delta x becoming larger, okay, then the uncertainty, or say the distribution of the momentum in the x direction, becomes smaller. Okay, so now we actually also understand a little bit more about what does the single diffraction actually mean, and is actually really closely connected to the uncertainty principle Heisenberg actually proposed. And if we use the mathematics which we learned from last time, the C function is going to be proportional to integration from minus d over 2 to d over 2 dx exponential minus I kx minus x. And if I have d goes to infinity, which means that you have an infinity wide slit, okay? Based on the formula which we have derived last time, basically we will see that C function as a function of kx is going to become a delta function. And this delta function is delta kx. All right, so that means if you have absolutely no idea about the position of the electron, all right, you are going to get very, very precise information about the momentum in the x direction is actually going to be equal to 0. Because it's a delta function, it's only non-zero at kx, which is the direction of propagation equal to 0. Any questions so far? Okay. So from those experimental results, we found that the probability, okay, the probability of getting a hit on the screen is proportional to psi 1 squared if I only have the first slit there, okay? That means the probability P is proportional to psi squared. And this is actually probably one of the most crazy results in the physics we learned so far. In some sense, it's kind of sad as well. Why is that? This means that, okay, I can calculate those wave functions. And the probability of getting an outcome at a specific position is proportional to this wave function squared. Okay? But I feel maybe demoted, right? Because originally we are like, God, you know, you can predict, okay, I have this thing, this object, and then I have force, and then it goes like, oh, like this way. I can calculate the trajectory of this track thing over the brace as a function of time, and I know what is going to happen. I have the full control of all the objects which I have in my hand, in my experiment, right? But now, quantum mechanics or this experimental result tells me that we can only predict the probability, the odd, right? Instead of the outcome. You see my point? I can only predict the wave function, the distribution of the wave function, and the probability of getting a result here is proportional to the wave function squared. But I cannot predict the outcome before I do the experiment. That's really a big change in your view, or say in our current understanding of the physics. You can say that maybe Yen-Jie is not working hard enough. Maybe all those electrons which are emitted from the light source, from the electron source, already made up their mind where this electron is going to. For example, electron number 1 is doing this, going here, and electron number 2 already made up its mind, it's going to do this, and the electron number 3 is maybe do this, and then all those trajectories are already determined, and there are hidden variables which Yen-Jie doesn't know. Therefore, he screwed this up and said, oh, come on, we can only predict the probability, right? But the thing is that from the experimental result number 2, experimental result number 3, and number 4, you can see that the electrons cannot make up their mind when they are emitted, right? Because when they got hit by the light, the electrons cannot know in advance that it is going to be hit by a light, right? And the light can be a very, very mild, very, very small energy, so that it should not affect the predetermined path of the electron. Do you get this? Right? So that doesn't make sense. So it is not because Yen-Jie is not trying hard. It is really because nobody can really tell before the experimental result is actually shown or the measurement is already done. Okay? If you can find any case, all right, maybe we will win another 100 Nobel Prize because you are showing that the whole understanding of quantum mechanics is not correct. Really. Okay, please tell me when you actually have done this experiment. I will be very proud of you, for sure. All right, so now we are actually in a position to discuss this result. So now actually we can also make use of this understanding and predict what will be the particle probability distribution in a potential well. Suppose I have an experiment which I have a well where I have potential goes to infinity in the left-hand side or right-hand side edge of this well. And I will define my coordinate system so that the well is actually at x equal to 0 or x equal to L. All right? So by now, when you see this is really looks really familiar to you. In the center part, you have some kind of translation symmetry, and at the boundary, those are forbidden region. You cannot actually have a particle there because the potential is infinity, right? Therefore, this is actually giving you boundary conditions. Of the wave function, describing the state of the particle inside this box. So the boundary condition will be psi 0 will be equal to 0 because it's actually at the left-hand side edge of the well where you have infinite potential. And also, you can have psi L, this will be equal to 0. Right? Because the right-hand side edge, you also have infinite amount of infinitely high potential. Right? Therefore, when you see this, your immediate reaction will be Now I know what is this. This is actually psi n. The solution to this problem must be something like psi n of x should be the normal mole of this system, and it's going to be an sine kmx, where kn will be equal to m pi divided by L, where n is a number, can be 1, 2, 3, goes to infinity, right? By far, you have actually learned all these practical calculations from the previous examples we had. Therefore, what would be the psi n x as a function of time? Then what I'm going to get is an sine kn x exponential minus I omega mt. Of course, we can also really plot all those results. So for example, n is equal to 1. Basically, what you are getting is like this. Doesn't surprise you, right? This is actually psi as a function of x. And n equal to 2. This will correspond to the situation where you have one node in the middle, right? Etc., etc. You can have many, many higher m value solutions. And what would be the probability to find the particle in a specific location? As we mentioned before, the probability is proportional to wave function squared. Therefore, the probability will be proportional to sine squared knx. And what we are going to get is like this. If I plot n equal to 1, this is p as a function of x. The probability of getting a particle at a specific place, if we are looking at the situation in normal mole number 1, that is like this. You are much more likely to find a particle in the middle of the box. On the other hand, we can also plot the probability as function of x for n equal to 2 case. If we are actually operating in a second normal mole, then basically you have some distribution looks like this. In this situation, it is forbidden, or say there's no zero probability you will find the particle in the middle of the box, etc., etc. You can actually calculate all those corresponding probability distribution as a function of m value and as a function of position. Okay? Sounds like a very good story, but there's something missing, right? What is actually missing? You have the normal modes, you have the Kn. What is missing is the wave equation, right? The wave equation is missing, right? You don't have the dispersion relation. This solution is incomplete. You don't know what is actually the omega value, right? Because you don't have dispersion relation. So what is actually the wave equation for the quantum mechanics? So it is actually Schrodinger's equation. So Feynman once commented on the origin of the Schrodinger's equation. It's from where? It's not possible to derive it from anything you know. It's just coming out of the mind of Schrodinger, actually. So there's no reason, and it works. That's the beautiful part. So what is actually this equation? So this is the equation Schrodinger actually write down. It's like I h bar from Planck constant, partial t, psi xt, and this will be equal to minus h bar squared over 2n, partial square, partial x squared, plus v xt, psi xt. Okay? So this is really nice, and it works and matches with experimental result. And now I have already the normal mode. I can plug that into this equation to see what I can actually learn from there. So what I'm going to do is to plug in psi n xt into this equation to get the dispersion relation. So what is actually the dispersion relation? So here I have partial t. So I extract 1 omega minus I omega out of this. Then basically I get h bar omega n psi n xt in the left-hand side. Okay, I'm plugging in psi n into this equation and see what happens. Then this will be equal to, I also know that in the middle of the box, okay, V is actually the potential. Okay, the potential is 0 inside the box. The potential is infinity at the edge of the box. Okay, therefore I can safely ignore this term to be equal to 0. So you have a free particle inside the box. And what is actually this term? This term will give you minus h bar squared over 2n. Okay, I have a double differential of x, and therefore I get basically minus km squared, right? Because it's sine theta, right? So basically I get minus k squared, so therefore I cancel this minus sign. I have kn squared out of this calculation, and I still have psi n xt here. Okay, I can cancel these two. Then what I'm getting is that omega n is equal to kn squared h bar, right? I cancel one of the h bar here, all right, divided by 2n. This is actually the dispersion relation of the wave function. De Broglie proposed the wavelength of the wavelength of the matter wave is actually highly related to the momentum of the matter. So basically, he proposed that P, the momentum of the particle, is actually equal to h bar k, where k is the wave number of the matter wave. Okay? If you accept de Broglie's interpretation, basically what we are getting is something really, really interesting. If we put together this dispersion relation and the de Broglie's interpretation of matter wave, what I'm going to do is to calculate the group velocity of this dispersion relation. So I can now calculate group velocity Vg will be equal to d omega dk, right? And I know that omega is equal to h bar k squared divided by 2n, right? This is actually equal to h bar k divided by n, right? Everybody's following? Okay. And this is equal to what? This is equal to P divided by M if I use de Broglie's matter wave. Okay? Therefore, you have P equal to M times Ng. Wow! Look at this. What are we getting here? What we are getting here is that the group velocity of the wave equation, okay, of the waves, is actually the classical velocity, P equal to n times v. Now everything actually is becoming more and more clear. We know and we learned already from AO3 what is actually the meaning of group velocity. The meaning of the group velocity is the speed of propagation of a wave package, right? Remember our discussion before about AM radio, right? So what is actually the speed of propagation of the wave packet is the group velocity. So now we have solved the problem. Why electron can be a particle at the same time, also like waves. It is actually described by wave functions. The classical behavior we see on the electron is because it is actually described by these wave packages. It's pretty localized, and the motion of this wave package in a free space is actually the speed of the propagation is the group velocity. Therefore, there's no contradiction between the classical calculation and the wave interpretation of the electron. So that really surprised me really very much. And you can see that given the dispersion relation, you can see also this is a rather dynamical result. The wave function, the real part of wave function is actually blue, and the imaginary part is actually red. It's actually oscillating up and down. And the oscillation frequency, by now you know, is governed by that dispersion relation. Okay, now actually everything seems to make sense now. Really, really very cool. So on the other hand, we also have to live with probability density, right? So you cannot tell the exact position of a particle anymore. You cannot tell the exact outcome of an experiment anymore. And that is actually to do with this interpretation. And all those phenomena at very, very small scale is actually described by quantum mechanics, which we will learn some more in AO4. And also in the future, it will be governed by the quantum field theory, which is actually for the future. And what is actually the life living with quantum mechanics and quantum field theory? So this is a very simple Lagrangian of the standard model, right? And it describes everything except the gravity, okay? And it's really simple. It's called standard model, right? And look at this part. This is governing the Higgs decay to Z boson, all right? And without the experimental result, we don't really know what is actually the mass of the Higgs. It's a missing observable before. And on the other hand, as a particle physicist or as a high energy nuclear physicist, I have no idea about what will happen in the next collision. Why is that? You know the reason now, right? Because we cannot predict the exact outcome of an experiment. It's all governed by wave functions. Therefore, what we are doing is the following. We are doing the brute force. So we collide like crazy. Collide like crazy until something interesting pops out. That's actually what we're really doing, okay, as a particle physicist. And this is actually a beautiful event from proton-proton collisions. at the Large Hadron Collider is a Higgs 2Z boson event. And one of the Z boson become the two red line, is actually the two muons. And the other one decays to two electrons, which are detected by the calorimeter as the two blue things there. As a high energy nuclear physicist, I am interested in the production of quark-gluon plasma from lead-ion collision. So I am now putting together two ions, have them collide, and I hope that by chance I can deposit a huge amount of energy in a very small volume. And then I would like to see this crazy matter actually gradually expand and become a lot of particles. And I study those particles to understand what would be the nature of this material, which starts to exist in the very early part of the whole universe history. Just 1 microsecond after the Big Bang, we are having the whole universe filled by this crazy material. And we are creating this in the experiment, and we will only be able to hope that, okay, by chance, I have the collision happen. By chance, I have a very high density environment. Somehow, multiple quanta decide to scatter from each other, and they deposit energy in a very small volume. And we collect all those spectacular events to study the property of all those little Big Bang. So that is actually the consequence of this wave function interpretation. So now, coming back to this standard model, this really simple one, you can see that it's a theory of almost everything, but except the gravity, really sad. So if you can actually put them all together, then you will also win a Nobel Prize, and giving you all those ideas so that I can have a very good student winning the whole Nobel Prize. Of course you will. And now I would like to discuss and use the remaining maybe 10 minutes to discuss with you the gravity. So here is actually something related to gravity. So Einstein actually predicted that the distortion of the space-time generated by objects can travel through the space, okay? I don't have the derivation here because it will take another maybe 2 hours to do this. But I would like to ask you to trust me. This is actually a result coming from general relativity. And you can see that when we can actually generate gravitational waves, and I can actually do the generation here, right? Like this, I'm rotating, I'm generating gravitational wave. And that student in the back is also generating. Yes, you are. Yeah, you are generating. Everybody is generating. You are also generating. Yeah, very good. But the problem is that the space-time distortion is really small for people who are not very massive, like me, right? So that's a problem. So I can generate, I'm doing the demo here, but doesn't help. You cannot really detect them. And even Einstein himself think it's impossible to detect them, maybe in our lifetime, right? And what will be the outcome of the calculation? The outcome of a calculation, if you have a gravitational wave passing toward you, okay? So what it does is the following. So basically, the space is distorted in a way such that it first expands in this direction, and then expands in the other direction, perpendicular to the original distortion. And if you put an array of particles, the circular array of particles, and look at what is going on, when the gravitational wave passes through it, it passes through the array in this direction. What you are going to get is an effect like that. Okay? Of course, this is actually highly exaggerated, right, in this setup. You don't really see this kind of sizable distortion when Yen-Jie is dancing around, all right? Okay, so how about we actually visualize this thing? The problem is that we cannot really see the space distortion, but what we can actually see is the light which actually pass through those little distortions. So this is a simulation from LIGO collaboration. They are simulating the merging of the two massive black holes. And you can see that they are rotating to each other, with respect to each other. They are radiating energy out of this two-body system. Let's take a look at this again. So this is actually a simulation of the event observed by LIGO. So both black hole have a mass roughly 30 times of our sun. Okay, it's very massive, and they are rotating with respect to each other, and generate space-time distortion. And you can see that the space-time distortion stop after they merge each other, and we were hoping that we can detect those. How crazy is that? Okay, so how do we detect them? Actually, you already have the knowledge to design the experiment to detect this kind of effect. So remember, the effect of the gravitational wave is like this. So you have distortion like this, right? What we actually NIT and the Caltech and the many other collaborators designed the LIGO experiment. So what is actually LIGO? It's a laser interferometer gravitational wave observatory. It is actually always good to have a very good name of your experiment, right? So that is actually LIGO. So what actually it does is the following. So basically, it emits the laser, and it split the laser into two pieces, and there were mirrors in the very far end, refract those lasers, and they come together, and there is a detector, detector, which detects the interference pattern of these two optical path lengths. Wow, sounds familiar to you, right? Hey, you already know how to explain this to your friends already. Really cool. And in order to have redundant measurement, for example, if you only have a single experiment, maybe one graduate student is like, oh, doing dancing, next to a detector, then you see some fake signal, right? And that's not going to be helpful, right? So what it does is that basically we have two experiments. One is actually in Hanford, the other one is actually in Livingston, and they are actually 3,000 kilometers away from each other, so that there should not be any correlation between the signal coming from earthquake or dancing of the graduate students or whatever, right? So they can actually use that to suppress any coincidence, which is actually not related to gravitational waves. So what does this do? Right? So now we have all the knowledge to actually explain this phenomena. So what this does is the following. So it emits the laser, and when the gravitational waves comes in, then it does this space-time distortion, and then the interference pattern of the waves going through different optical path lengths is going to change. So you can see that originally the experiment is designed so that you have complete cancellation, but when the gravitational waves is actually hitting the site, you will be able to see that really you will have constructive interference at some point because of the movement of the mirrors, and those mirrors are really, really far away from the source. It's like each of them is actually like 4 kilometers away from the mirror. And due to the incredible precision which were achieved by this experiment, we will be able to detect the signal of gravitational waves. So you can see again from here, right? So basically, when the gravitational wave comes in, first you split the light source into two pieces, have then hit the mirror, which is actually 4 kilometers far away from each other, and they come back. And initially, the experiment is designed so that very precisely there will be no amplitude detected by the photodetector. And when the gravitational waves comes in, it actually really change the length, right, between the splitter and the mirror. Therefore, you will see light constructive interference even from the photodetector. So that is really cool. And this is actually the experimental result. Look at this. You actually can see that LIGO actually achieved the sensitivity. The gravitational wave was first observed on September 14, 2015. And the LIGO is actually announcing that in the February 11th, earlier this year, right? And what we actually see from here is that this is actually, as I mentioned to you, there are two measurements, two sides. The left-hand side is actually the measurement from Hanford, and the other one is actually the measurement from Livingston. Okay, so there are two different curves, and they all have exactly the same, almost exactly the same pattern. Of course, the time is actually shifted because they are in different places on the Earth. They are 3,000 kilometers apart, so therefore there will be a shift in time. And this is actually the time-shifted result. And you can see also the calculation below, which is actually what you should expect if you have the merger of the two massive black holes. So you can see that they are actually rotating with respect to each other. One of them is actually 29 times larger than the mass of the sun, and the other one is actually 36 times larger than the mass of our sun. It's that precision, okay? And they generate theoretically this kind of pattern, and this is actually really detected by both LIGO experiments, which they are 3,000 kilometers apart from each other. Okay, so I think this is really a historical moment that we actually were very lucky to live in this moment. What does that mean? That means we have a new way to really hear about what the universe is actually trying to tell us. We have a new way to detect phenomena which is actually really happening very, very far away from the Earth. How far is actually this event? This event, according to calculation, is actually something like 2 billion light year, 1.3 billion light year away from the Earth. And we can detect them. And we even know the mass of the two black holes. Wow, what does that mean? This is really crazy to me and really exciting because we are opening up. Okay, I have 2 years and it's opening up another year in my brain. And that is actually the way to hear the gravitational wave with the experiment we perform on Earth. Okay, so I hope until now, I have convinced you that this is really not the end of vibration of waves, which is actually the name of AO3. Instead, this is actually just the beginning. you have a lot more to explore when you take general or special relativity course. You have a lot really more to explore when you take quantum mechanics. And I hope you really enjoy the content of this course. Personally, I really enjoy that very much. I love this course, and I hope you also love it and understand something from my lecture. And thank you very much. And the next time, we are going to have a review of all concepts we have learned from AO3 next Tuesday. Thank you. Thank you very much.